The proximity fuse, the VT secret weapon. In the Pacific Island campaigns of 1944, American forces noticed something remarkable. Japanese kamikaze attacks, which had terrorized earlier operations, were being defeated with unprecedented effectiveness. Anti-aircraft fire that previously required hundreds or thousands of shells to down an aircraft was now achieving kills with far fewer rounds. In the Battle of the Bulge, German attacks faced artillery fire of devastating accuracy that seemed impossibly effective. Allied aircraft were being shot down at alarming rates by anti-aircraft fire that seemed to explode with uncanny timing. Behind these developments was a secret weapon so closely guarded that its very existence was classified at the highest levels. It was the proximity fuse, officially designated the variable time or VT fuse, and it represented one of World War II's most important and closely guarded technological breakthroughs. This miniature radar system, small enough to fit in an artillery shell and rugged enough to survive the massive acceleration of being fired from a gun, revolutionized anti-aircraft warfare and artillery fire. This is the story of the fuse that changed warfare through precision timing, electronics miniaturization, and security measures that protected its secrets even from friendly forces until its capabilities couldn't be concealed. The proximity fuse's story begins with a persistent problem in anti-aircraft warfare, hitting fast-moving aircraft with shells that had to be timed to explode at precisely the right moment. Traditional anti-aircraft shells used time fuses set before firing to explode at estimated altitude. But estimates were often wrong. Aircraft maneuvered unpredictably, and timing had to be perfect. Exploding too soon or too late meant the shell was harmless. Studies showed that thousands of anti-aircraft shells were being fired for each aircraft destroyed, an appalling inefficiency that meant aircraft often got through to attack their targets. What was needed was a fuse that could detect when the shell was near a target and automatically detonate at optimal range. This required miniature electronics that could survive being fired from a gun, experiencing forces up to 20,000 times gravity, could function reliably despite the extreme conditions, and could detect targets and trigger detonation within fractions of a second. Multiple nations worked on proximity fuse concepts before and during World War II. British researchers made early progress but lacked resources to bring concepts to production. German scientists developed acoustic and optical proximity fuses but never achieved reliable results with radio-based systems. It was American researchers and industry, supported by substantial funding and British collaboration, who developed the VT fuse into a weapon that could be mass-produced and deployed. The development program began in 1940 when British researchers shared their work with Americans, hoping American industrial capacity could accomplish what Britain couldn't manage while fighting for survival. The National Defense Research Committee, a U.S. government organization coordinating military research, established Section T specifically for fuse development. Led by Merle Tuvey at the Carnegie Institution in Washington, D.C., Section T brought together physicists, engineers, and manufacturers to solve the unprecedented technical challenges. The concept was straightforward, but implementation was extraordinarily difficult. A miniature radio transmitter and receiver in the nose of the shell would emit radio waves, and when reflections from a nearby target reached sufficient strength, the fuse would trigger detonation. This required miniaturizing transmitter, receiver, antenna, and detonation circuitry into a package small enough to fit in a shell nose, rugged enough to survive the gun launch, and capable of functioning reliably in all weather conditions. The vacuum tube technology of the 1940s seemed completely unsuited to this application. Vacuum tubes were fragile glass components that would normally shatter under the shock of gun firing. They required precise voltages to operate. They were relatively large. Every aspect seemed incompatible with artillery shell requirements. But Section T researchers developed specialized rugged vacuum tubes with reinforced construction that could survive gun launch. These tubes, far tougher than commercial tubes, represented a breakthrough in rugged electronics. Power supply was another challenge. The fuse needed electrical power, but batteries wouldn't survive gun launch. The solution was ingenious. Use the firing setback forces to generate electricity. When the gun fired, a small generator spun by the acceleration produced electrical power that charged a capacitor. The stored energy powered the fuse's circuits during the shell's flight. This self-powered design eliminated batteries and ensured the fuse was safe to handle. It only became active after firing. Safety was critical. A fuse that might detonate accidentally would be too dangerous to use. Multiple safety mechanisms ensured the fuse couldn't detonate until after launch and until it was safely away from friendly forces. Mechanical safeties locked the detonation circuit until launch forces released them. Electrical safeties prevented detonation until the fuse had traveled far enough from the gun. Multiple redundant systems ensured reliability while preventing accidents. Testing was extensive and dangerous. Shells fitted with experimental fuses were fired at drone aircraft to verify detection and detonation. Early tests showed promise, but also revealed problems. Some fuses were too sensitive, detonating prematurely, while others were not sensitive enough, missing targets. Environmental factors, rain, sea spray, electrical interference, affected performance. Each problem required analysis and redesign, a process that took years. Production required unprecedented precision. The fuses contained miniature components manufactured to tolerances far tighter than conventional electronics. Assembly required skilled workers using microscopes and specialized tools. Quality control was critical. Every fuse had to work reliably because failure meant both a wasted shell and a missed interception. Despite these challenges, American industry eventually produced proximity fuses at rates exceeding 70,000 per day. The first operational use of VT fuses came in January 1943 when the cruiser USS Helena used them against Japanese aircraft in the Pacific. The results were immediately apparent. Aircraft that would normally require hundreds of shells to destroy were being shot down with a handful of VT fused shells. The dramatic improvement in anti-aircraft effectiveness transformed naval air defense. The security surrounding VT fuses was extraordinary. Their existence was top secret. Initial use was restricted to naval warfare over water, where unexploded shells would sink without providing evidence to enemy forces. Use over land was forbidden, because unexploded duds might be captured and reverse-engineered, compromising the technology. This restriction meant that for the first year and a half of operational use, VT fuses were exclusively naval weapons. Captain Frederick Moosberger, commanding a destroyer squadron in the Pacific, described VT fuse effectiveness. "In the first time we used them, we were amazed. Japanese aircraft that would normally press home attacks through our anti-aircraft fire were being shot down before they could reach release range. Our gunnery became far more effective almost overnight. We didn't understand exactly how the new fuses worked, that was classified beyond our clearance, but we knew they were changing the odds dramatically in our favor." The Battle of the Philippine Sea in June 1944 provided dramatic demonstration of VT fuse effectiveness. American carrier task forces, equipped with VT-fused anti-aircraft shells, faced massive Japanese air attacks. The battle, later called the Great Marianas Turkey Shoot, saw Japanese aircraft shot down in huge numbers. While pilot skill and fighter defense were factors, VT fuses contributed significantly to the lopsided American victory. Japanese aviators, already depleted of experienced pilots, faced anti-aircraft fire far more deadly than anything they'd encountered before. The security restrictions eased in December 1944 during the Battle of the Bulge. German forces had broken through American lines in the Ardennes, creating a desperate situation where every weapon was needed. General Eisenhower authorized use of VT fuses in ground artillery despite the risk of capture. The results were dramatic. VT-fused artillery shells set to detonate above ground created airburst effects that were devastating against exposed infantry and vehicles. German forces faced artillery fire of unprecedented lethality. The Germans did capture some unexploded VT-fused shells during the Battle of the Bulge. German technicians examined them and recognized the sophistication, but by then it was too late to develop countermeasures or copy the technology.
The war ended before Germany could respond. Post-war interrogations revealed that German scientists were impressed by the fuse's sophistication, but acknowledged they lacked the industrial capacity and resources to replicate it.
The technical achievements represented by the VT fuse were remarkable. The fuses contained miniature radio transmitters operating at approximately 180 to 220 megahertz, receivers sensitive enough to detect weak reflections from distant targets, amplification circuits to process signals, timing circuits to determine optimal detonation moment, and detonation circuits to trigger the explosive. All these systems had to function in a package measuring about 5 inches long and 2 inches in diameter, capable of surviving gun launch forces that would crush most electronics. The manufacturing process required precision that seemed impossible at the time. Vacuum tubes had to be assembled with reinforced filaments that wouldn't break under shock. Circuitry had to be miniaturized and potted in compounds that protected components while allowing them to function. Antennas had to be designed to survive aerodynamic forces while providing adequate radio performance. Each fuse was tested electrically before shipment, but there was no way to fully test function until actual use. The cost per fuse was substantial, approximately $20 in 1940s dollars, equivalent to over $300 today. This was many times the cost of a conventional time fuse, raising questions about cost effectiveness. But analysis showed that VT fuses were economical. If a VT fused shell cost $50 total, shell plus fuse, but achieved kills with 1/10 the ammunition expenditure of conventional shells, the VT was cheaper overall. The analysis didn't even account for the value of protecting ships and troops from attacks that would otherwise succeed. The psychological impact on enemy forces was significant. Japanese pilots facing American ships equipped with VT fuses found that their attacks were being disrupted before they could reach effective range. Aircraft that pressed through anti-aircraft fire were being destroyed at unprecedented rates. The survival rate for kamikaze attacks dropped dramatically when American ships employed VT fuses, affecting Japanese tactics and morale. German forces facing VT-fused artillery in the Battle of the Bulge and subsequent operations experienced devastating airburst effects. Artillery shells exploding overhead, scattering shrapnel downward, were far more lethal than shells exploding on impact with the ground. German infantry learned that foxholes and trenches providing good protection against conventional artillery offered little safety against airbursts. The psychological effect of facing this new threat contributed to declining German morale. The technical limitations of VT fuses were significant, but manageable. They didn't work well in heavy rain as water droplets reflected radio waves and caused premature detonation. They could be affected by electrical interference. They were more complex than simple time fuses, requiring more careful handling and storage. They couldn't be used in some situations where friendly aircraft might be in the area, as the fuses couldn't distinguish between friend and foe. Despite these limitations, the overall effectiveness made VT fuses invaluable. The post-war impact of proximity fuse technology extended far beyond military applications. The miniaturization techniques, rugged electronic design, and radio technology developed for VT fuses influenced numerous civilian and military developments. The proximity fuse represented an early example of integrating sophisticated electronics into harsh operational environments, a challenge that remains relevant today in everything from smartphones to spacecraft. The security lessons from the VT fuse program influenced subsequent weapons development. The careful compartmentalization of knowledge, the restrictions on use to prevent enemy analysis, and the security measures protecting the technology became models for later classified weapons programs. The ability to deploy a secret weapon for over a year before enemy forces realized it existed demonstrated that proper security could protect technological advantages even during widespread use. The industrial achievement represented by VT fuse production was remarkable. Taking a laboratory concept and scaling it to production rates of over 70,000 units daily required unprecedented coordination between research, development, and manufacturing. Multiple companies, including Eastman Kodak, Westinghouse, Crosley Corporation, and others, participated in a massive production program that delivered over 22 million VT fuses during the war. The quality control challenges were immense. Each fuse had to work reliably, as failures meant both wasted ammunition and potentially failed defense against enemy attacks. Statistical quality control methods pioneered in American industry during the war were essential to maintaining standards while producing at massive scale. Rejection rates were carefully monitored, and processes were continuously improved to enhance reliability. The logistical demands of VT fuse deployment were substantial. The fuses required more careful handling than conventional ammunition components. They needed protection from moisture, extreme temperatures, and mechanical shock during shipping and storage. Special training was required for personnel loading shells. Despite these challenges, the logistics system successfully delivered millions of fuses to combat theaters worldwide. The scientific legacy of the VT fuse program extended to many participants' post-war careers. Researchers and engineers who worked on VT fuses went on to prominent positions in academia, industry, and government. The experience of solving unprecedented technical challenges under wartime pressure proved valuable in post-war careers. Many VT fuse veterans contributed to early computer development, radar improvements, and other electronic innovations. The declassification of VT fuse technology after the war allowed public recognition of the achievement. Technical articles described the fuse's operation, and its contribution to victory was acknowledged. But during the war, the achievement remained secret even from most military personnel who used the fuses. Sailors and soldiers knew the new fuses were more effective, but not how they worked or why they were so closely guarded. Dr. Merle Tuve, who led Section T, later reflected on the program. We knew we were working on something important, but we couldn't fully appreciate the impact until we saw combat results. When reports came back showing how dramatically VT fuses improved anti-aircraft effectiveness, we knew the effort had been worthwhile. The technical challenges had been immense, but we'd overcome them through collaboration between scientists, engineers, and industry. The VT fuse program showed what could be accomplished when research, development, and production worked together towards a clear goal. Comparison with other nations' proximity fuse development reveals American advantages in both research and industrial capacity. British researchers made crucial early contributions but lacked resources to pursue development during their most desperate period fighting for survival. German researchers understood the concept and attempted development, but never achieved reliable radio-based proximity fuses, partly due to resource limitations and partly due to different technical approaches. Soviet forces, despite receiving some VT fuses under Lend-Lease, didn't develop their own during the war. The American success reflected substantial research investment, industrial capacity, and effective collaboration between government, academia, and industry. The strategic impact of VT fuses, while difficult to quantify precisely, was significant. In naval warfare, the improved anti-aircraft effectiveness protected ships and personnel from air attack, allowing operations that might otherwise have been too costly. In ground warfare, the artillery effectiveness improvements helped defeat German counterattacks and supported Allied advances. The fuses didn't win the war single-handedly, but they contributed meaningfully to victory while saving Allied lives. The cost-benefit analysis of the VT fuse program shows massive returns on investment. The program cost approximately $1 billion, a substantial sum, but only a tiny fraction of overall war expenditure. The benefits included protecting ships worth billions of dollars, saving thousands of lives, and enabling operations that might otherwise have failed or cost more casualties. From a purely economic perspective, the VT fuse program was one of the war's best investments. From the concept of using radio waves to detect targets and trigger detonation, through the technical challenges of miniaturizing electronics to survive gun launch, through the massive industrial effort to produce millions of fuses, through the security measures that protected the technology from enemy knowledge, through the combat effectiveness that changed warfare, the Proximity Fuse program represented American scientific, industrial, and organizational capabilities at their best. The VT fuse, officially called variable time to obscure its true nature, was one of World War II's genuine secret weapons, a technology so advanced that its use had to be restricted to prevent enemy discovery, yet so effective that it changed tactical outcomes wherever deployed. It represented the intersection of pure research, applied engineering, industrial production, military necessity, and operational security. The proximity fuse deserves recognition alongside better-known technological achievements like radar and the atomic bomb, as a weapon that changed warfare and helped secure Allied victory.